Hello everybody, this is going to be a review of the concept of intermolecular forces, and at the end we'll practice identifying what type of force is present, like we did in Honors Chem. So the reason why intermolecular forces are important to us is because it really determines how things behave and what state of matter they would be in at various temperatures. Meaning, is it a solid, a liquid, or a gas? When things are at room temperature, if they have pretty good, strong, attractive forces, the substance will end up being a solid or a liquid. The stronger the forces, the higher the boiling point, the higher the melting point, the thicker it is. It's more viscous, so it has more surface tension. Those interactions between molecules tells us how it behaves. If they are being held close together, you'll have to give it more energy to pull them apart. So if a liquid has a lot of intermolecular forces, you'll have to put a lot of energy in to separate them into gas particles. The intermolecular forces are a result of the attraction between opposite charges. Now, it's not like in an ionic bond where we have a full positive and a full negative, necessarily. It can be, but it could also be a slight partial positive from a polar molecule to a slight partial negative side of a polar molecule. Even nonpolar things will end up having a little bit of attraction due to the temporary charges they can form from the electrons randomly moving around. We'll look at that more later. Intra, with an A, intramolecular force would be what's holding these atoms inside the molecule. Intermolecular forces is when we're looking at molecule to molecule. They are not nearly as strong. The larger your charge, the stronger the attraction. And the longer the distance, the weaker the attraction. Does that remind you of a law that we learned about, right? Reminds you of Coulomb's law, right? Everything's about attractions and repulsions. But in intermolecular forces, they're relatively small compared to the actual bonding that's happening inside the molecule. We don't have full positives and full negatives, it's just slight ones, little partial ones, and they're much further apart. And like I said, the more attractions there are, the stronger the attractions, the more energy it takes to separate those molecules. When you boil a liquid, you have to put enough energy in to overcome all those attractions. We're not breaking the atoms apart inside the molecule. We're not breaking the actual covalent bonds. We're separating the molecules far enough. We're overcoming the intermolecular attraction between molecules so that they can be spread apart, so that instead of a solid or instead of a liquid, they would now be a gas. You can look at boiling points to understand and figure out which thing has stronger IMFs. Normal boiling point is what it's called when the vapor pressure, the pressure of the particles at the surface, is equal to the atmospheric pressure. Remember that the air is pushing down on the surface of your liquid. And so for something to boil, we have to get to the point where the particles coming out of the liquid have the same pressure as the air. You should remember some of these IMFs. We learned about London dispersion forces. This is temporary. They are not permanent. We have a brief moment in time where the electrons are in an unequal distribution. And then in the next moment, the electrons move and it's gone. Very small and very temporary. Compare that to dipole-dipole, which are permanent unequal distributions due to the electronegativities and the three-dimensional geometry of the structure. It's permanent. Water will always have a dipole because the 3D shape and the arrangement of electrons and the electronegativities all results in a permanent situation where one side is more positive than the other. A special type of dipole-dipole is hydrogen bond. If you had me for honors chem, you'll remember me telling you how I think hydrogen bond is a terrible name. I wish it was hydrogen force. That's kind of the joke a lot of chemistry teachers say. It's a very strong dipole-dipole when you have hydrogen attached to something very electronegative. Not a lot of things are electronegative enough to count. So we say that it has to be one of the NOFs, nitrogen, oxygen, and fluorine. And then they typically need to have lone pairs on them as well to give even extra electron density. It's like a dipole-dipole is a magnet and a hydrogen bond is a super crazy strong magnet. That's kind of the idea. Sometimes you will have to rank them in a relatively generic way. The strongest thing that you might come across would be what's called a network covalent. There are not very many of these. You need to remember carbon as graphite and diamond, silicon dioxide, some of those silicon products, hydrogen bonding, dipole-dipole, London force. You can see how small these things are compared to something crazy super strong like a network. And can you see on kind of a generic hydrogen bond would be quite stronger than a dipole-dipole. That's why it's so special. Remember, hydrogen bonding is really important in biology applications like DNA. Let's practice identifying some of these. You can pause the video if you need a little more time than I'm giving. So what type of IMF is in water? Well, I know that that is a polar substance. So there's going to be London forces since everything has London forces. But because it's polar, it will also be dipole-dipole. But it's a very fancy type of dipole-dipole because it has hydrogen bonded to oxygen, which has lone pairs on it. So that makes the dominant IMF the strongest, most important, the most impactful IMF present, hydrogen bonding. Compare that to ammonia. Ammonia is NH3. Nitrogen connected to 3 hydrogens with a lone pair on that nitrogen is polar. And it meets the criteria for a hydrogen bond. Now let's look at hydrochloric acid, HCl. That's still a polar molecule. So it's at least a dipole. But does that meet the criteria to be a hydrogen bond? Nope. Chlorine is not electronegative enough. You cannot get a big enough difference in partial positive and partial negative. So it's just a regular old-fashioned dipole-dipole. Yes, it's silly, but you do need to say the word dipole twice. Carbon dioxide, if you remember, is a linear molecule. It is nonpolar. So nonpolar things are only going to have London dispersion forces. Every once in a while, those electrons will happen to end up on one side more than the other. And for that brief moment in time, you'll get a little bit of partial positive and a little bit of partial negative, and you'll have a very teeny tiny, weak, and temporary dipole. What about CH4? That's tetrahedral. There's no lone pairs on that carbon. It ends up non-polar, so it's London dispersion. Can you see how I have to remember my Vesper shape and I have to remember my polarity to be able to do IMFs? If it takes you 5 minutes to draw a Lewis structure, and another 5 minutes to know your Vesper shape, and another 5 minutes to know if it's polar or not, you're never going to finish. You have to be familiar enough with some of these that it doesn't take you very long to come up with the polarity. Now this is tricky because you don't have a formula, do you? You got to remember how to get your formulas. Hydrogen sulfide is H2S. When you draw the Lewis structure, it ends up bent like water, but it's not strong enough to be a hydrogen bond. Sulfur is not electronegative enough, so it's just a regular old dipole-dipole. In the next lesson, we'll talk a little bit more in depth about the theory behind these, what's actually happening, how they interact, how you can make predictions based on the different IMFs. But I hope this review helped you remember some of the IMFs you learned in Honors Chem and some of the factors that we're interested in, like boiling point and melting point and things like that are because of the IMFs. All right, everybody, that is it. I hope that was helpful. Bye.